Think about the following question. Given a finite field denoted f sub q of q elements and an integer n greater or equal to 1, how many n by n nilpotent matrices are there over this finite field? Here, by nilpotent matrices, we mean the matrices that will vanish after taking certain powers. Specifically, the matrix A is called nilpotent if A raised to the power L is equal to 0 for some integer L. And let's fix the notation here. We denote the set of all n by n matrices over FQ by m sub n of FQ. And the set of all n by n nilpotent matrices over FQ by nil sub n of FQ. So this is our notation for the set of all nilpotent matrices with coefficients in F sub q, this finite field of q elements. And we will use this notation henceforth. This is a hard question. The first resolution to this question is in the year 1985. Mathematicians Fine-Herstein proved that the number of nilpotent matrices n by n over FQ is equal to q raised to the power n squared minus n. Which solves this question. However, the proof that we are going to talk about today is due to another mathematician. In 1960, mathematician Gerstenhaber gave another elementary proof that we are going to talk about today. Before we start, let me first introduce a couple of notations and definitions. For a positive integer k, let the k by k matrix n sub k be such that every entry is 0 except for the first diagonal of the main diagonal, where we put all ones in there. You can view this as a Jordan block where the diagonal entries are all equal to 0. And recall from the linear algebra that if you raise this matrix to the power k, you get 0 matrix. So as a result, this matrix is nilpotent. And in particular, for this integer n fixed at the beginning, we let capital N denote the matrix n sub n for simplicity. And now, for any n by n matrix A over the finite field Fq, we let L of A to denote the collection of matrices such that ny is equal to ya, where this n is n sub n, namely this type of nilpotent matrix with k equal to n. And sometimes we'll informally call this condition that y nil commutes with A, because this equation tells you we will multiply y on the right hand side by A, you will get back y with n multiplied on the left, and this n is the standard nilpotent matrix. Or we may also call this that A nil commutes with y. With this definition at hand, we introduce the next one. Let script A be the union of all L of A, where A ranges over the collection of all nilpotent n by n matrices over Fq. And the matrices in this script A will be called admissible matrices. With those notions introduced, we are going to talk about a couple of lemmas that will lead to the resolution of this question or a proof of Fine-Herstein theorem due to Gerstenhaber. But before we do this, let me first tell you what the general idea of the proof is. The general idea is the following. Instead of counting the number of nilpotent matrices over Fq directly, we are going to count this number, m of y, defined as the number of nilpotent matrices A, such that A nil commutes with y, namely this relation. As you can imagine, this is something that is more general and stronger, because when y is equal to 0, M of 0 is just as same as the number of nilpotent matrices over FQ, the number we want. What we will do is that we are going to find the relation among M of y for all y's, including the case when y is equal to 0. And we will use the information for M of y for all other y's to get this very number, M of 0. And that is to say, in order to achieve our goal, we first want to make our life harder by studying something that is seemingly more complicated. Well, that is usually the case in mathematical research. The statement of a problem might look very simple, but the solution to it can be very hard.